All right, now we're going to go back to talking about these electric lines of force. We call them E-lines because we're lazy, right? So these E-lines, all they are is really, they're like a map, okay? They just give you an idea of the direction of the electric field and the magnitude, okay? That's all. I mean, they don't exist. I already said this, right? They just give you magnitude and direction. So let's just figure out kind of how we figure it out. So here we have this sphere of negative charge. Now remember, the probe charge or the test charge is always positive. We just keep it simple. So what we do, we take a positive probe charge and we just kind of move it around. Right? We just move it everywhere, okay? And so, so here's a positive. Remember, this is supposed to be super small, so this doesn't have any effect on this, okay? So as small as you need it, all right? So it doesn't push this thing or attract this thing or anything like that. Okay, now, what is the direction of the force that this positive test charge feels from this? What's the direction of the force? Well, obviously it attracts, right? So the force is that way, right? Okay, so what you do, you just take this positive, you just keep putting it all over the place, all right? And then you answer that same question. What's the direction of the force that this feels from this? And obviously, you know, you're going to get lines like that, right? Because wherever you put a positive, it's going to be attracted to the negative. Okay? So these are called electric field lines. All right? They give you the direction and the magnitude of the electric field. Now, here's a whole bunch of electric field lines, right? And so, wow, what's the deal with that? Well, so where's the electric field going to be stronger? Well, what do you think? I mean, it kind of makes sense that you have a whole bunch of field lines here, and they're all close to one another. So that's where the electric field is going to be strong. Here, you know, they're not so close to each other, so the electric field is going to be weaker. So that's kind of how you look at it. So we have some electric field rules, all right, rules. So here they are. Okay, so the tangent to an electric field line at any point is the direction of E at that point. What? Okay, so here's a point, right? Here's a point, and you draw the tangent line, and that's the direction. Well, that's sort of easy because it was a straight line, right? Well, let's give something that's not so straight. Okay, here. So here's a plus and here's a plus, right? And so look, so here's the E field line, and you if you want to know the direction of the E field right there, right? What do? You just figure out the direction of the tangent line, right? So the tangent line right at this point is that. Okay, so that's what it means, number one. The tangent to an E field line at any point is the direction of the E at that line. What if we want the direction of the E field right here? Well, then you just draw your tangent line, right? It's going to be something like this, you know? Okay. I mean, here's another one. Here's a dipole, right? Plus minus. So here's the E field line. I want to know the direction of the E right here. Tangent. So it goes like that, right? It's going in this direction and tangent. Okay. E field is stronger where the E's are closer together. So it's going to be really strong here, weaker out here. Strong here, weaker out here. Strong, weak, you know. It kind of makes sense, right? The E field goes as 1 over the distance squared. Kind of makes sense. There's only one value of E at every point. I mean, that sort of makes sense, right? I mean, that's like, well, I don't want to say that. Okay, so it just means at any point, there's only one value of the E field. You can't have two values at the same point. That doesn't make any sense. And then, okay. E field lines begin or end on charges. Now, that's not totally true, so we'll revisit this later. But for now, we're just going to say that is true. Okay, we'll talk about it later. So E field, look at it. See how this begins on the plus and it ends on the minus. Yeah, I don't want to talk about that one. All right, so they're going to curve, you know, it's going to curve. Okay, so those are your E field rules. So let's see if you understand them. All right, so okay. So the tangent to any E field line at any point is the direction. Stronger where there are more E field lines, closer together, only one value beat in every point. They begin or end on charges. Okay, so we have the 4 patterns shown. Assuming there are no charges in the regions shown, that's important. Which of the patterns represent a possible electrostatic field, E field? All right, so pause your video and figure it out. Okay, let's talk about it. E field lines begin or end on charges, as far as we know now. Well, that means that it says there's no charges here. Well, this would indicate that there's a charge, right? So this is impossible. Okay, here, what in the world is this, right? This is like a negative, but this is a positive, so this is kind of like a, I don't know what I'm talking about, right? So this is impossible, because this would have to be a charge here. That's ridiculous. Now let's see. Now this, how about this? Remember, we learned that the E field lines begin or end on a charge. Well, I don't see, there can't be a charge here, so it can't really, this is impossible, right? It has to begin and end on a charge. This is impossible. What's the only one that's possible? The only one that's possible is B, right? This is the only one that's possible, right? It has to be a charge somewhere to the left, has to be a charge somewhere on the right. That's all we know, you know? Okay. All right, we want to now talk about, so we're going to learn some E fields of certain objects that we're going to use a lot. We've already learned the E field of a point charge. We're going to use that a lot. Now we're going to learn the E field of a charged plate. So here's a plate. It's really assumed to be very, very large. And it's charged. It's uniformly charged. And we're not going to prove it. We're just going to say this is how it is, all right? So here's the plate, all right? You know? And the E field, what do you notice? It doesn't change. It's completely constant, or it's completely uniform. You know, like the E field of a point charge, you know, the point charge E field was KQ over the distance squared, right? So it changed very much. The further you get away, it gets smaller, smaller, smaller. Here, it's constant. It never gets smaller, never gets bigger. It's constant. So here's the chart. So here's the E field. So let's say that this plate has total charge Q. So the E field of a plate is total charge Q divided by 2, epsilon 0, that's that constant that we'll get to one of these years. And then A is the total area of this thing. And it points away from the plate. Okay? So there it is. So it's a uniform, constant E field. Now, what do we care? Well, you'll see. All right, so here's a question for you. The magnitude of the electric field associated with plates 1 and 2 is, I just wrote it down, right? Or I just showed it to you. So the E field of a plate is Q over 2 epsilon naught A. See, look at that epsilon naught, right? So that comes from the K, remember that constant K. All right. With the direction as shown, right? If this is positive, it goes away. Okay. When 2 oppositely charged plates are placed parallel to one another, the magnitude of the electric field is what? So here's my suggestion. Draw a picture showing all the E field vectors inside and outside the plates. So what I'm suggesting you do is draw something like this. So here's your positive plate, here's your negative plate. Draw all the E field vectors here, here, and here, and figure it out. So everybody, please, this is important. Pause your video and figure it out. Horrible. All right, let's go through it. So what's the E field for a positive? It's uniform, it points away. What's the E field for a negative? It's uniform, it points towards. I didn't need you to draw that. I just forget that. So I'm like towards, right? Now, these have the same charge, just opposite, right? Same charge. They have the same charge, they have the same area. So that means that if the E fields magnitudes are exactly the same. Well, what happens here? You have out, to the right, you have to the left. They cancel, right? So there they cancel. Here they cancel. Here they add. Okay? So in other words, this is the E field of a charged plate. Between them, you double it. So between the plates, the E field is twice that. So the E field is just Q over epsilon naught A. Ta-da! Right? So between the plates, Q over epsilon A, outside is 0. So here's a nice, all right? So this is called a capacitor, a parallel plate capacitor. This is plus Q, this is minus Q. That's the E field between them. Notice it's uniform, right? Completely, perfectly uniform. Capacitors are used all over the place in electronics. They used to be used in keyboards. When you press a key, you would change the physical characteristics of a capacitor. So here's a nice picture, right? So inside, the E field goes from plus to minus, right? So they add. Here they cancel. Here they cancel. There you go. So this is called an ideal capacitor. Nice, constant, uniform E field. Inside, nothing. Outside. Yeah. By the way, in biology, you learn about cells. Cell membranes act like capacitors. Many years ago, I taught Physics 220, which is electricity and magnetism calculus based, in the summer. And a bunch of the students were medical, pre-meds. And they took the MCAT, and they were shocked, and so was I. A lot of the physics questions were about capacitors on the MCAT. But anyway, yeah, I don't want to say that. I don't know about that yet. Okay, let's talk again about the electric force. We keep talking about this thing, right? So here's our famous equation, which we're going to use again and again and again. F equals QE. All right, so here we have this beautiful capacitor, right? The E field lines go away from the plus towards the minus, nice and uniform. So the E points to the right. So if I put a plus charge in here, what's going to be the direction of the force, or what's going to be the direction of the acceleration? Well, F equals QE. E points to the right, Q is positive. What's positive? Right. It's right, right? So the force is going to be to the right, the acceleration is going to be to the right. On the other hand, if I put a negative particle in here, negatively charged particle, what's going to be the direction of the force, or what's going to be the direction of the acceleration? Well, again, E points to the right, but Q is negative, so what's negative right? It's left. So the force or the acceleration and the acceleration are going to be to the left. That's all. Now, all right, that's fine. That's just the direction. But, we usually want to know the magnitude, right? So let's discuss the magnitude. You're going to see in Physics 105 again. All right, let's do the magnitude. So, most important equation. Forget that. Most important equation, physics, classical physics anyway, F equals ma, right? All right, so therefore, A equals F over m. Now we're saying that the electrical force is QE, so we have QE over m. Now, we're going to talk about a constant electric field, right? So we're going to pretend we're inside a capacitor, or between the plates of a capacitor. So that means that E is constant. Well, Q is constant, M is constant, so this is constant, right? So it's constant in one direction only. So what have we learned about if we have something moving and there's acceleration that's constant in one direction and it's 0 in another direction? What's the trajectory of that? Physics 105, right? It's parabola, right? This is just what we learned in projectile motion, right? Projectile motion, we have gravity this way, and there are no other forces, right? Once you throw something and you let go, the only force is gravity. So we have constant force this way, no other forces. And we learned that parabolic trajectory. Well, here it's a negative. All right, so E field is this way. Shoot a negative object in it. What's going to be the direction of the force? Opposite to the E field. It's going to be this way. So there's no other forces, right? The force is this way. That's all. And so this is just going to be a nice parabola. So everything you learned in Physics 105 applies. Okay. All right, so that's kind of cool. All right, now we're going to talk about something that seems to be unrelated, but we're just introducing it now so we can learn more. We're going to use this later on. Okay, so here, this is a solid conductor. So think of it as a piece of, I don't know, brass or copper or something like that, right? Solid brass, solid copper, worth a lot of money. Okay, so it's a conductor, and we only want to look at the situation where it's an electrostatic equilibrium. All right, now what's equilibrium mean? Physics 105, right? Equilibrium means that the sum of the forces equals 0. So that means that there's, that means something could be moving at uniform velocity, right? But look, but we also have electrostatic. What's static mean? Static means the velocity equals 0, all right? So this says basically the acceleration is 0, but the word static means that the velocity is 0 as well. So basically nothing is moving, okay? So no, if there are any charges, they're not moving, right? Electrostatic equilibrium. So we want to talk about this because we're going to use it later and now. All right. So another way to say this, so the charged particles are not moving. So we can also say there's no current. Wait a second, current? What's current? Well, current is just the movement of charges, right? Like you have a wire. You have a current through the wire. What's that mean? It means you have negative charges moving through the wire, okay? So the current is just the flow of charge. So this is an electrostatic equilibrium, so we have nothing moving. So we have no charged particles moving individually or as a bunch. We have no currents. Nothing's moving. All right, so here we go. We want to discuss this crazy thing. Okay, so if we want electrostatic equilibrium, what has to be true about the E field inside? Let me give you a huge hint. Okay, so I asked, we want electrostatic equilibrium. So no forces, no accelerations, no velocities. Everything is 0. So what has to be the E field inside? If we want the sum of the forces to be 0, and what has to be true about the E field? 0, right? 0. Okay, so the E field has to be 0 inside. If the E field were not 0 inside, then there'd be forces, so things would not be in equilibrium. Okay, so E field is 0 within the conductor. All right, now let's say this thing is charged. I don't care what charge, negative or positive, doesn't really matter. Let's say it's negative just to make it easy. Let's say this thing has a net negative charge. So where are those negative charges going to be? Remember, negative charges repel, right? So they want to get as far away from each other as possible. So where are they going to be? On the surface, right? On the surface. Okay, so because you can't get any further away, right? So all excess charge resides on the outer surface of the conductor. All right, that makes sense. Okay, now, so think about it. So we have all these, let's say, I don't care, let's say positive charges, all right? Change my mind. So let's say we have positive charges on the outside of the conductor. What's going to be the direction of the E field? So let's just say that this is the top surface of the conductor, all right? And we have all these positive charges. Well, what's going to be the direction of the E field? Well, you know, let's just pick a number, right? Pick a direction. So let's just say, I don't know. Let's just say it's in that direction. All right, I don't know. All right. Well, whatever. Okay, well, what do you do with a vector that's not along some desired direction? You resolve it into components. So we can resolve this into a piece that goes like that, and a piece that goes like that. All right. Now, look, you can't have an E field parallel to the surface. You can't. Why not? Because if you had an E field parallel to the surface, and you have F equals QE, what would happen to these positive charges? They'd be accelerated, which you can't have. It's equilibrium. So you can't have this. Well, if you can't have this, that only leaves that, right? And so basically what we're saying is that the electric field on the surface always points perpendicular to the surface, because then you guarantee that the charges don't move, right? Okay, so the E field vectors are perpendicular or normal to the surface of the conductor. All right, well, now you might think this is a crazy question, but just hold on. Okay, earlier I said this was a solid hunk of copper, right? Or whatever, brass. But now let's just say we have a cavity inside, okay? So we have, inside there's this cavity. It doesn't have to be a spherical cavity, any kind of cavity you want, So what do we do there? It's an empty cavity. Well, empty cavity, right? Well, we know that the electric field here is 0, right? Because we already know that the E field is 0 within a conductor, and then there's no charge in here, so it has to be the E field in there. Our favorite number, 0, right? Now here's kind of a cool picture. So let's say that this is our conductor, right? Big hunk of copper, but it has a cavity in it. You could take this big hunk of copper, put it between the plates of a capacitor. So, you're putting it, where there's a nice big E field, But I don't care what you do with it. The E field inside this cavity has to remain 0. Now you say, who cares? Well, a lot of people care. All right, okay, let's hold on. So E is 0 inside any empty hole. Now, why do you care? Well, have you ever ordered like a motherboard or some sensitive piece for a computer? If you ever order something like that, you'll notice it comes in these anti-static bags. Because, the components are incredibly sensitive to E fields. If somewhere along the line, or between the shipper and you, it gets exposed to a fairly decent E field, it could destroy the thing. So they put it in an anti-static bag, which is basically like this. Okay? So, in other words, this is the conductor, and then you have a cavity inside, and it doesn't matter what happens outside. The E field inside is going to be 0. So the anti-static bag acts like a conductor, and therefore the E field inside is going to be 0. Ta-da! That's kind of cool, don't you think? All right? And here's something else, something practical. Okay, let's say you have a metal car. I have to say that nowadays because not all cars are metal like they used to be. So you have a metal car, you're inside the car. Well, this is a conductor, right? And you're inside the cavity. So if the car gets struck by lightning, if you're inside, not a problem. On the other hand, if you're not using your head, or your brain, I guess I should say, and the car gets struck by lightning, and you touch it, well, goodbye, right? You're going to be not feeling well. All right? So there's 2 applications of that. So this is called electrostatic shielding, all right? So they actually coat these bags with some kind of a conductor. So it really is a conducting surface. It even says it, conducting, I don't know what that is, something bag, right? So that is basically that, right? So it's really cool. All right, let's talk about the electric dipole. We're going to talk about this later. I tell you, this chapter is really setting us up for a lot of the future chapters. Okay, so again, what we want to talk about is a dipole. So what we're really talking about are molecules, dipole molecules. And H2O is an example of it. But we just want to have a model that kind of covers all of them, And so this is our model that covers any kind of a dipole molecule. So we have a plus and a minus, and they're somehow attached. I mean, they're not really, so we're just going to pretend there's this massless pole or something like that, all right? So it's a unit, all right? This is a unit. This is a unit, right? So this is a unit, all right? There's a model. Okay, so there it is, right? So this is our dipole. Here's the plus, here's a minus, and we're pretending it's somehow attached because it's a unit, It's a unit. So so D is the distance between them. Again, this is the minus Q, that's the plus Q. Now, let's say we have some external E field, all right? And let's just say the external E field points to the right. Like just, this could be like, let's say this thing is between a giant capacitor, So this is the, right? All right, so here's a plate, and here's a plate, okay? So we have this uniform E field that points to the right. This is like a big positive plate, this is a big negative plate, all right? So we get this uniform E field. All right, well, let's see. What's the net force on the dipole? The net force on the dipole. Well, use our famous equation that we're going to use all the time. So the electric field is to the right. This is the positive charge. What's positive right? It's right, okay? So the force is to the right. Here, it's a negative charge. So what's negative right? Negative right is left. So the force is to the left. Now, these charges have the same magnitude. The electric field is uniform. You can tell it's uniform because see how the distance remains the same between the lines? That's how you know it's uniform. So that means that this magnitude equals that magnitude. So the net force is 0. Okay, whoopee! But, come on, what happens to that dipole? I mean, think about it. So here's the dipole. This thing wants to go to the right. This here wants to go to the left. What's it going to do? It's going to go like that, right? It's going to rotate, right? So what does that bring up? Torque, right? Torque, okay? So the torque is going to cause it to move like this, okay? Because it wants to be right there, So the torques are going to cause it to rotate. And we're going to discuss this in gory detail later on, but not now. Okay. Let's see. An electrically neutral dipole. That's kind of a dumb thing to say. Look at, as far as we're concerned, the dipoles are always neutral because this magnitude is the same as that magnitude, okay? So in Physics 106, the dipoles are always going to be neutral. But anyway. I guess in the real world, you could have this like maybe 2Q and this like 1Q, but all I'm saying is our model in Physics 106 is always going to be the same magnitudes, so they're always going to be neutral. Okay, let's go. An electrically neutral dipole is placed in an external field, that means electric field. In which situations is the net force on the dipole 0? So figure it out. Pause your video. Okay, it can't be this because it's not it's a non-uniform E field. So the force here will be different from the force here because the electric field is different. Same thing for this. Here, it's a uniform E field, so the force here, magnitude, will be the same force here, magnitude. Right? And it'll be opposite, equal and opposite. Same thing here, uniform E field, so the forces will be equal and opposite. So the answer is 5. 5. Okay, that is the chapter. Let's review. So hopefully we became familiar with basic electric phenomena. Two charges, plus and minus, conductors and insulators. Talked about the charge model, talked about conductors and insulators. We talked about this cool thing called polarization, right? Attraction between large, put quotes around the large, neutral objects and charged objects. Coulomb's law, gosh, we're going to use that a lot. Superposition for electric forces, just that electric forces are vectors, so you add vectors, nothing new there. We talked about the field model, concept of the field, a force field. You know, when Faraday came up with the idea, he didn't think it was real. It was just something that helped him visualize, you know, magnitudes and directions. But later on, people realized, my gosh, they're real. I mean, they're real. They carry energy. I mean, Maxwell's equations are written in terms of these real fields, so they're real. And then we learned the electric field of a point charge, you know, kq over r squared, or d squared. We also learned the electric field of a capacitor, which we'll use again and again, and which you'll use maybe in your biology classes. Okay, so rather than show you 50 million slides, review slides, I'm just going to give you this, because this is basically everything. A lot of equations. Okay, two kinds of charge, plus and minus, already said that. Like charges repel, unlike attract. Large neutral objects are attracted to charged objects. Charge is quantized. If you measure the charge of anything in the real world, your everyday world, it's going to be plus or minus n, which is an integer, times the electron charge, or the proton charge. Charge is conserved. The charge before you do something is going to be the charge after you do something, all right? Coulomb's law, remember, this only gives you the magnitude. That's why we have these absolute value signs here. You have to figure out the direction by using this. So this is magnitude, all right? So k, q1, q2 over the distance squared. Now I put r, who cares, r or d. Okay, k is 1 over 4 pi epsilon 0. You really want to remember that. Well, maybe not memorize it, but just be familiar with it, because later on we're going to start using pi's and epsilon. We're not going to use k's later on. And this is the easy way to remember, 9 times 10 to the 9th. The electric field, this is the definition of the electric field. The definition of the E field is the force between the charge that creates the electric field and the probe, but then you divide by the probe because you want the electric field only to depend on the charge that created it. E field of a point charge, kq over r squared. The electric field of a charged plate, q over 2 epsilon 0 a. Charge of when I say the E field of a capacitor, I mean inside, right? Because outside it's 0. So you have an E field of a capacitor, just twice that, and then this. And look at, you notice that this is the same thing as that, right? It's just algebra, but a completely different meaning. This is the definition of the E field. This says that if you have an external E field and you put a charge in it, that charge is going to feel a force. So yeah, mathematically these are the same, but they're different concepts. All right, so that's the chapter. Thank you very much.